From our formula for conditional probability, we get that the probability of A and B in general is the probability of B times the probability of A given B, and that it also equals the probability of A times the probability of B given A. Because the right-hand side of these equations are a product, we can visualize it by mapping it as an example of the multiplicative property. Here we can imagine that our different scenarios of A and B, A and not B, not A and B, and not A nor B, as a branching out process. The probability of traveling along these branches is the probability of going from one node to the next node. For this first branch, going to A is the probability of A. Likelihood going to A naught is the probability of A not happening. To go from A to B assumes that A has already happened. So it's a conditional probability, and it's asking about going to B. Similar, we get that this lower node assumes that A has happened and that we're going to B complement, and so on. Here we see that the probability of A and B is the product of the probabilities of its path, and so on. We also have that all the events branching off from a single node sum to 1. So of course the probability of A plus the probability of not A is 1, but less obvious, the probability of B given A plus the probability of B not given A is also 1. These relations allow us to fill in an empty table with very little information provided. Suppose we were told that the probability of R complement was 0.4, that the probability of T given R was 0.5, and that the probability of R complement intersect T was 0.12. This would be enough for us to fill in the entire table. We could start with what we know. Probability of R complement is 0.4. The probability of T given R is 0.5, and the probability of R complement intersect T is 0.12. Because we know that the branches of this node should sum to 1, we get that this should equal 1 minus 0.4, which is 0.6. Similarly, the branches of this node should sum to 1, so we have 1 minus 0.5, which equals 0.5. Because the probability of the entire path can be found by multiplying the probabilities of the branches, we get that the probability of R and T is 0.6 times 0.5, which equals 0.3, and that the probability of PR intersect T complement is also 0.6 times 0.5, which is 0.3. We can use a similar thinking to find what this missing branch probability is. We know that 0.4 times whatever this branch is should be 0.12. This means this branch is equal to 0.12 divided by 0.4, which equals 0.3. At this point, since we know that the branches of this node should sum to 1, we get that this is 1 minus 0.3, which equals 0.7, and we can fill in our final blank as 0.4 times 0.7, which equals 0.28. To check our final answer, we could see, does the probability of all our different outcomes sum to 1? Well, here 0.3 plus 0.3 plus 0.12 plus 0.28 does in fact equal 1.